To find the radius of the atom and the relation or mathematical relation between the radius of the atom and the A, it is helpful to actually imagine that this structure are a packed structure. So instead of small atoms like this, it's actually bigger in size, and therefore they are arranged in such packed structure where one atom will be exactly next to the other atom. Instead of having space like this, the actual structure is way more packed. And we can see for simple cubic, if this is a packed structure, the white dot will be bigger like that. The white dot over here will be bigger like that as well. And therefore, in this very edge, we will see two atoms neighboring to one another. And in this case, we can see that if we take the side, so this is A, this is also A, and here we will have R plus R. So for the case of simple cubic, we can write down that A is equal to 2R. Now let's take a look for FCC first. For FCC, if this is a packed structure, actually the atoms will be next to each other exactly at the face or the side. At this side, for instance, you know that this is A, that is also A, and this diagonal will be A and square root of 2. And from here, we can see that at this very diagonal line, we will see three atoms are packed next to each other. And we can draw it here like this. So if we take this is A, and this is the side, which is the diagonal A equal to square root of 2, then this is the R of the atom. So in this case, we will write it down as 4R, because here we have the R and also R over here. So we'll have 4R equal to A multiplied by square root of 2. A over 4 square root of 2. In this case, R is equal to A divided by 2. Next, for BCC, the packed structure will be found actually in the diagonal inside the cube. And if we take this particular square, where this is A, and this is A multiplied by square root of 2, this will be A multiplied by square root of 3. So in this case, we can write it down like this. We have A square root of 2, and this will be A square root of 3. So we can write down that in this case, this is also R, this is the midline, and this is also R. So again, 4R will be equal to A square root of 3. So R itself will be equal to A divided by 4 square root of 3. So depending on the arrangement, either the simple cubic, the BCC or FCC, we can find the relation between the radius of the atom and also the A or the edge of the cube. So from here, we can substitute the A cubic to R. For the case of SC, A can be replaced with 2R, so 2R now power to the third. For the case of BCC or body-centered cubic, the A can be expressed as square root of 16 over 3 multiplied by R. So we can substitute this into this. And for the FCC, we can substitute the A with square root of 8 multiplied by R. And we can also fill this into this value, and don't forget to power to the third. So we get the volume, and with this approach, we will get the density of each of the cubical arrangement. That is important to remember that they are actually a closely packed structure where the atoms are neighboring with one another. And regarding this neighboring principle, we also recognize the term of coordination number. Coordination number is the number of atoms which are the immediate neighbor or the closest neighbor of an atom in the structure. So let's take a look at our cube again over here. Now we can calculate the coordination number or Cn for each of the arrangement. Now, for a simple cube, we can see that the atom is over here and it is surrounded by 1 to the back, 1 to the left, and 1 to the bottom. And of course, because this unit is actually a repeating unit and what we only see here is only one cube, but they are actually formed of several different cubes closely packed between one another, we can also imagine that there is another atom up here at the top. So also 1 on the front part and 1 on the right part. So we can calculate the immediate neighbor for this atom, that would be 1 to the back, 1 to the front, 1 to the left, 1 to the right, 1 to the bottom, and also 1 to the top. So we actually have 6 neighbors, so the Cn will be 6 for a simple cubic. Now let's take a look at the body-centered cubic. For body-centered cubic, the easiest atom to count the neighbor on would be the one in the middle. You can see the one in the middle is being the closest to 1, 2, 3, 4, 5, 6, 7, and 8 atoms, and therefore the coordination number would be 8 for the BCC. Now finally, for the FCC, it's a bit tricky. You have to really imagine that this is only a single cube that we are seeing here, and this is being repeated into other cube at the front, other cube at the upper part, other cube at the left, and also other cube at the bottom left, upper left, and so on. So if we take this particular spot over here at the corner, at the left corner, the closest neighbor would be the one at the sides. This is closer than the one at the other corner, because this is A and this is only half of A multiplied by square root of 2. So this is actually the closest. And you can imagine that we have another side. We have a side over here. We have also another side to the front part. So if we call this the right part, so this is back right. We also have the front right. We also have the back left and the front left. So just by this facing to the top part, we will have 4 neighbors. 1 there, 2, 3, and 4. So that's the first side. The second side would be the one that I highlight over here. So at this part. Let's call this bottom right. You also have top right, and then top left, and bottom left. So there will be 4 more neighbors. And finally, this side that is facing us right now, the one that I highlight, and let's call this bottom right. We also have up here top right, and then over here bottom left, and over here top left. So in total, you will have 4 times 3 or equal to 12 neighbors. And this is indeed the coordination number for the FCC. If you have trouble imagining this, you can write or you can draw several cubes stacking to one another. And then you can check again the coordination number that should fit to these numbers that are given to you right now.